And that's certainly allowed mathematically, because the dark energy explanation is based on the fact that we assume everything's fairly smooth, we're not sitting in a special place. I currently don't think that explanation works, because it requires us to sit in a relatively empty part of the universe that's very empty and very large, and looking further beyond us in the universe, we don't see any other regions, we don't see any regions that are so empty and so large. So the jury is still very much out on dark energy. That's very embarrassing. So that's 75% of the universe we've got no idea about still. Coming back a bit to the 70%, coming back a bit to the 25% of dark matter, the evidence for that's much stronger, because we've seen it happening in many different ways. And having eliminated so many possibilities, there's now the chance that we're going to make some real progress on that with the particle physics experiments, notably the Large Hadron Collider in CERN in Switzerland, which potentially can test some of the ideas that the particle physics people have, saying that there's some particles that they can generate at these high energies that could actually have the right properties to explain the dark matter that has this gravity effect but is not detectable any other way.
Right. Some of our space assets, notably WMAP and maybe even COBE, have actually sort of verified some of the latest thinking and evidence for the accelerating universe. Could you perhaps talk about a little bit about that?
Yeah, this whole subject is quite amazing in the way that we're using information from opposite ends of the universe almost. So these satellites you referred to, COBE is the Cosmic Microwave
Background Explorer, yeah.
Yeah, and WMAP is the Wilkinson Microwave Anisotropy Probe. Anyway, the basic idea is they're satellites that are measuring low-frequency radio signals emitted relatively soon after the Big Bang. And they're up above the Earth's atmosphere to get to remove distortions and to get rid of the atmosphere. But the key thing is they're very sensitively and uniformly measuring the strength of this radio signal across the whole sky. It comes in all directions to us, literally from very soon after the Big Bang. And the incredible thing they've done is measure the small irregularities in that distribution. You have to be very sensitive to see this. The first measurements of the microwave background thought it was smooth across the sky, but it's not. And we're very relieved that it's not. If it was smooth, there would never have been any irregularities around which, like seeds, you could later form galaxies and planets and people. So the irregularities were needed to form structure in the universe, but also there was this, as predicted, a pattern in that distribution due, as it turns out, to pressure waves moving through the early universe and then stopping when it's got to a certain temperature. That pattern is actually what forms the wiggles we look for in our project. But 10 years ago, they found that pattern in the microwave background, confirming the theory that it was there and giving us this measure we can now use for the other experiment. So they measured that pattern, and they could use that to triangulate how light traveled through the universe until it reached us, because they knew the length of that pattern back at the Big Bang, and then they just follow the light till it reaches us. And by measuring the angle, they work out how light travels across the universe. And the amazing thing they confirmed is that basically the universe is geometrically flat, so that on average the light travels in straight lines. Sounds pretty obvious, but until they measured it, we didn't know if that was the case or not. And showing the universe was flat was one of the main things we had to find out about the universe. So those experiments showed that it was geometrically flat. The same time, early galaxy surveys were showing us how much normal matter there was in the universe. And those two things together showed you that either the universe was very young, or you needed something extra in the universe to give you an older universe. And then the supernova results came in and said there's something making it accelerate. And the three things together, when you do the calculation, then tell you you have an old universe that's old enough to contain the globular clusters.
So what does that do for the Hubble constant then?
The Hubble constant is just one of the factors we use to describe the universe, and it's saying how fast it's expanding. It's always been the case that we call it a constant, but it's actually, it can change at different periods in history, but from a human perspective, it's pretty constant at the moment. I will get back to that question.
It's a variable constant, right?
If you look back in time, the universe is expanding at a different rate. So, and that's one of the nice things we can do with our experiment. We're actually going to go back in time and measure the Hubble constant at 10 billion years ago.
Right, that's going to be good, because I think from memory we're down to something like 73 kilometers per second per megaparsec, I think, or something like that. There's
right.
WMAP has constrained that to around about 1% or possibly even 0.1%, but it's pretty tight, and it does certainly confirm that value. Again, I think WMAP and maybe even the Sloan Digital Sky Survey has been one of those two astronomical or space satellites that have actually really given a huge boon to the astronomy fraternity.
Oh, and, yeah, very much so.
And maybe going back to maybe another one of those space assets, I mean, in terms of choosing your galaxies to actually look at, maybe you can talk to us about perhaps GALEX, the Galaxy Evolution Explorer, possibly together with the Sky Digital Survey or any of the other surveys that went into actually making up the mix for your project.
Yes, that's a very good question. We have to come to this telescope with a list of galaxies already on hand that we actually then want to measure the redshift or distance for. And we've been extremely ambitious for what's now a modest-sized telescope in not the best site in the world. We're actually trying to measure distances to galaxies halfway back to the beginning of the universe. And we have to be very clever to find galaxies that will make that job easier. And what we're doing is selecting galaxies that are very active. They're actively forming new stars. And so they have a lot of very hot gas that has, when we look at the spectrum, has very strong features that we can detect even at these huge distances. We have these strong features which will make it easy to look at the spectrum and see, yeah, the features move that much, so we can measure the redshift. Average galaxies won't have those strong features, so it's too hard at these incredible distances. So we need galaxies that are very active, forming new stars, and have these emission lines, we call them. And another property of galaxies like that is there's so much hot gas that they give off a lot of ultraviolet light. So a really easy way to find them is actually to use an ultraviolet camera. Fortunately, our atmosphere, fortunately for this sort of astronomy, our atmosphere doesn't let the UV through, so you've got to go up above the atmosphere. And we've done a deal with an American team running a NASA satellite called GALEX. It's basically a very clever ultraviolet camera in orbit that's surveying nearly the whole sky. And so they very kindly agreed to provide data to us, basically mapping out some very large regions of the sky with their ultraviolet camera to help us find the galaxies that give off the most ultraviolet, which will therefore have these lovely features that will let us measure their distance. So the GALEX people have very kindly given us the images of the sky where we can pick out these galaxies giving off the ultraviolet. Then we need to go to a ground-based telescope for two more things. We need an very accurate position, so we can know where to put the optical fibers in precisely, and we need their colors with the ground-based telescope to help us weed out the nearby galaxies. So for the northern half of our survey, we're using imaging from the Sloan Digital Sky Survey, and then for the southern half, we're using data from a similar survey run by a Canadian team from the University of Toronto.